All right. So in the previous video, we talked about this layout, right? This layout of a simple file system, and this was our own this is our implementation of our file system, right? From so I told you we skip the boot block to keep things simple. We have super block, inode blocks, fs bitmap block, inode bitmap blocks, indirect blocks, and data blocks. So try and understand this when we see the code, the implementation of it. Um, the super block, like I said, stores information about our file system. So we have a magic number, which is a special signature that identifies our file system. We have the number of inodes, total number of inodes in our files, and inodes are just data representation of our files and directories. Then we have total number of inode blocks. This inner inode block stores the inode itself, right? So the inode block stores the inode itself. And I told you that each block, like each block in the each inode block will store a particular number of inodes. So each inode block will store 128 inodes. So to get total number of inodes in the file system, multiply it by 410, which is the total number of inode blocks, and we get 2418 inodes. Then right, so we say that the size of our inode is 32 bytes, right? Location of bitmap, right? Bitmaps are just forms of the data structure that keeps track of the state of an object. Like I said, it keeps tracks of the state of an object, and this object in this case our blocks, right? Keep track of the state of our blocks. So fs bitmap will keep track of the state of all blocks in our file system on our disk, right? And inode bitmap will keep track of the state of all inodes, right, in our file system. So that's what that does. Then indirect block is like a, should I say, a kind of pointer that stores the address of other data blocks. So if our file was very, very large, we might make use of this indirect block. But for now, we might sideline it now because we don't make use of it because our size is our file is our disk is actually very, very small, right? If our disk was to be large, we could make use of these indirect blocks. Then we have data blocks, and this is pointed to by the direct field. So we'll just understand this properly. Start going through the code. Okay. Alright, so this is the code of it. This is the code. Alright, so first thing is this is our file system, right? Our emitted file system. So it has explicit methods first, but what I want to first go through, the other file of the file system so you can understand better this, right? So you can understand the file system better. So first thing is that we have our macros, right? So this defines if this is a file, right? This is one. Just give it a value. Then file max size. This is going to be like 7 multiplied by 12. So we get the maximum number of maximum size of a file, right? The maximum size of a file. Then this is our magic number. So it could just be like a unique that's a unique value that identifies our file system. Then we have our blocks, total number of blocks in the file system, right? That's 496 blocks. So meaning that total size of our file system will be 16 MB because each block is about 496 bytes or 4 KB. So if each block is 496 bytes and we have 496 blocks in our file system, so that's going to be 496 times 496, and that will give us 16 MB. So we also have our inode blocks, right? Number of inode blocks, so we have about 410. And I told you that the inode blocks are about 10% of the disk space, right? So if you add 496 blocks, we have 496 block, 496 block. So 10% of this, 10% of 496 is, so 10% of 496 is 10% of 496 is sorry, so it's 10% of 496 about 4096.6, right? So that's approximately 410, right? So inode blocks will take 10% of the disk, right? Then number of inodes, right? So each inode is about 32 bytes, and altogether the total number of inodes in our file system is about 2489 nodes. So direct blocks per inode. So direct blocks per inode is actually where the file content or the content of the file will be stored, right? These are the data blocks, right? So direct blocks per inode means that how many should I say how many data blocks can be assigned to each inode. So maximum number of data blocks can assign to each inode is about six data blocks, right? So meaning that each inode will have a size of 6 times 496, right? And that's going to be what, 24 KB or so. So each inode will have a size of 24 KB if it was to be a file. Then we have super block, which is block 0. We have FS bitmap block 411. Then inode bitmap block 412, 413 for inode bitmap block 2, indirect block. So you don't really need to really get what is actually good. You also know that we have inode bitmap block that tracks the state of our inode, right, in our file system. So I told you again that an inode could either represent a directory or a file, right? If it's represent a file, the direct field of the inode, let me just quickly finish this here. So direct field of the inode will contain data blocks. If we represent a directory, the direct field of the inode will contain directory entry blocks, right? So I'll come back to this. So we have next thing is we have our magic number. So this is the super block, right? This is super block struct, and these are trying to store in the super block. We store it in the super block or magic number of blocks. So this is magic number. So I'm going to set this to this macro here, right? So it set this to this macro here. The number of blocks, total number of blocks we have here, right? Total number of blocks in our file system, which is 496 too. The number of inodes is 2480. Then super block, that is the address of super block itself, that's 0. The FS bitmap block, that's 411 here, and inode bitmap block 1 and block 2. So this is just information that the super block stores about our file system. So calculate the total size of this. I think this should be 16 bytes. So this is about 2, 1, 2, 3, 4. Yeah, that's 16 bytes. So total size of our super block struct, right, or object is 16 bytes, and that's supposed to be stored in the super block itself. So I told you that each block in the file system or the disk is about 496 bytes. So 16 bytes out of 496 bytes, right, is what to be stored, right? So this is what to be stored super block, and it could go eventually go to a larger size. The next one is our inode, right? So our inode contains fields like the type, the size, the direct, indirect. Although our inode is meant to be having more fields than this, but because we want it to be very, very simple, a very, very simple file system, we kind of strip down all the other fields, right? Probably in version 2 of the file system, I would implement things like read write, execute, and permissions, things like modification or timestamps, right? Location, things like timestamps, like things like when the file was created or when the directory was created, fields like when the file or directory was modified. Timestamp generally I'll implement a timestamp field. Then we also make use of this indirect field. Currently, like we don't really make use of this in our file system because our disk is very small. So we have the size, right? And this is keeps track of the size of the inode. So if this inode was to be a file, it will keep track of the size of the file, and which must not pass 24 KB, right, in size. Yeah, it must not pass about 24 KB in size. Then we also have directory entry. So this was if our file system implemented directories. For now, we don't actually implement directories in our file system to keep things simple. Again, in version 2, we actually implement directories and other features too, like journaling and those kind of things. But for now, we just keep it simple for now. So yeah, so these are also the functions we have, right? It's a large kind of has a lot of utility functions, helper functions, but the main function you can see here is starting from here up to this point. I can also include this too. So we have FS format. So FS format is actually to format our file system, right? So we create a disk path, FS mount, FS create, right, to mount our file system. So this doesn't really mount our file system, like it doesn't really do a mount, right? Actually, in real file systems, when we mount, we should actually initialize the root directory and start from there, right? But in this case, it's just like a helper guard to prevent us from creating files we've not formatted, to help us from creating moving files we've not actually mounted and stuff like that, so it prevents us from performing all these operations without mounting, right? So that's what this does. So before we go into the implementation of the file system, right, let's first look at the disk emulator. So since we don't have a physical disk, we have to try and emulate our disk, and we do that using a bin file. So the first thing we have here is open disk, right? And open disk contains a pointer to the file name. So what is the name of the file you want to pass? And the file should actually be in a bin file. It should actually be a binary file. Then the number of bytes of the file. So in this case, the number of bytes will be 4 MB, right? Because we're using that file to simulate our disk. So that's an emulated disk, right? So the size of our disk, right, will be 4 MB, and you pass the name of the file we create, right? So what teachers use, we make use of Unix code, right? Open to actually open the emulated disk, and open to actually open the emulated disk and other stuff like that. So we don't really need to understand. You just know that this actually opens or creates a file for us. So it opens a file if the bin file exists, and it creates a file if the file does not exist, right? It creates the bin file if it doesn't exist. So this actually simulates our disks, our physical disks. They have read block, right? For file systems, you can only read in blocks. We don't read in like bytes, read in blocks. So a block is about 496 bytes in this file system, about 4 KB rather. So we can read 4 KB at a time, right? And that's because we want it to be very efficient, and it also helps in things like paging when we start doing things like virtual memory and stuff like that. But do let us go into that. Then writing block, we also write, we only write in blocks too. For our file system, that's about 4 KB. We only write 4 KB at a time. Then sync disk is actually to sync all our buffers stored in RAM, in case if there's something like a power failure or some kind of termination of our process, we can sync it back to the disk, right? And close disk closes the disk, right? It closes the disk eventually. So that's the bin file. So that's just a basic overview of our disk emulator, right? So this just emulates a physical disk. Then we have our PFS, right? These are file systems. So this just exposes methods, right, that we call to actually like implement our file system. I can't really go through all of this code, but I'll just try and explain what they do, right? So first thing is that we have this variable global variable disk. So actually this should actually be stored in a struct, right, to keep this as should I say encapsulated, right? I don't use big terms because we're not object-oriented programming. We have to actually like try and store this in a struct to actually keep this private, right? So if you want to access all these variables, we should actually access them in the file system struct. But for now, we leave it like that. We'll actually try and I will modify it in later versions. So next thing is that we have our create cache, right? So when we read blocks from the disks, right, we have to actually look for a way to store it on RAM, right, so we can work with it, because reading from disks is actually very expensive, right? Reading from disks is actually very expensive. In fact, reading from disks is about 4 to, let's say, 100,000 times reading from disks is about 100 times slower than reading from RAM, right? So anytime you read from disks, you have to cache it in memory. So all these buffers are what actually caches all whatever we read from disks, right? So and each of these buffer have a particular function, right? So this shared cache actually caches about 496 or 4 KB of data blocks, right? We read from the disks. This actually caches our FS bitmap block. This caches our inode block, right? And this caches our super cache, which is actually the super block. It caches the super block, and this actually caches the inode block. So that's what this does. So don't confuse this inode cache and this inode bitmap cache. The inode bitmap cache caches the inode bitmap. The inode cache caches the inode blocks, right? The inode bitmap cache caches the inode bitmap blocks, and the inode cache caches the inode. So that's what it simply does. Then we have the FS bitmap init. So what we are trying to do in this FS bitmap init is that we are trying to should I say initialize the bitmap for our file system. So I told you the bitmap is what tracks the state of objects. So in this case, we are tracking the state of each disk block. So I'm going to read the block from memory, right? Read the FS bitmap from memory and store in the FS bitmap cache. Then what we now do is that we set this, right, set the block to have we set this to have a value of should I say 255, right? 255. So up to from 0 to 512, from byte 0 to 512, it will have a value of from byte 0 to 511, you will have a value of 255. So 255, what does this represent? This just represents something like 1 1 1 1 1 1 1 1 1, something like that, sure. So the first 8 bits, right? First 8 bits will represent eight data blocks in our it represent about 8 blocks in our file system. The next 8 bits will represent the next 8 blocks in our file system, and so on like that, sure. So we are going to initialize, allocate everything to free at first. When we initialize that, so we allocate all the blocks to free, all the blocks in our file system to free at first. Then inode bitmap need to also allocate all the inodes to free at first. So we have about should I say the size of this is 6,560. That's the size of our bitmap, right? Our inode bitmap. The size of our FS bitmap is 512. So 512 times 8 will give us about 496. So which means we are tracking about 496 blocks, right? And that's the total number of blocks in our file system. For the inodes, we are tracking about 6560 times 8, right? That's the amount we are tracking, right? And that's going to give us about, I think that's going to be 2,480, right? So this is what we are tracking, and we're going to allocate everything to 1. So we set everything to 1. So 1 means that all the inodes are free at this point. And for this FS bitmap cache, this means that all the blocks, right? All the blocks are initialized as what? As free, right? So our super block is free, our inode blocks are free, FS bitmap block is free, inode bitmap block is free, indirect block is free, and all our data blocks are free too. So next is shared cache. I didn't really make use of this. I think I didn't really make use of this. I will move the function, so I'll move this later on. So get current entity. How do I explain? Get current entity just help us to get the what does this do again? This actually help us to get the entity number, right? The position of our bitmap, the correct bitmap. So this actually is by search bitmap, right? To get the proper bitmap we have in our file system. So one thing is that we pass the entity number, right? And we pass the bitmap we want to actually search through. So we know we have about 2 bitmap. We have our FS bitmap, right? And we have our inode bitmap. So this FS bitmap here, this inode bitmap here, and so we pass the bitmap cache into it, and we want to check which objects are actually free or allocated. So that's what this actually does. So you see the get correct entity, search bitmap, mark bitmap. These are actually what we use to actually like check if an object, it could be a disk or an inode, is actually like allocated. So if we pass the inode bitmap to this place, to this point here, to this bitmap T, and we pass probably a number. So let's say we want to check for inode 3, right? We want to check if inode 3 is actually free. We get the correct entity, right? So get correct entity is to make sure that if the bitmap pass is a bitmap cache, FS bitmap cache, if it's actually a FS bitmap, if a file system bitmap, the total number of entities we must have must not be more than 496, meaning that must not have more than 496 blocks. So if someone passes like 4,000, sorry, if someone passes like 4,100 and something blocks, or 4,100 blocks, to actually error out, right? To not give us the right thing to actually error out, because the total number of blocks we can have in the FS bitmap is 496, so it must always be less than that. So we have our search bitmap, which actually searches the bitmap to check for any free inode, and this is going to be used in FS create. The map bitmap actually is used to allocate bitmap and deallocate bitmap. So what it does is that it actually like deallocates a block and allocates a block. right? Or you allocate an inode, or they allocate an inode. So this is just some logic. So this is just a technique that actually used to actually get the to get if a bitmap is actually to get to actually allocate a bitmap, either to allocate a bitmap or to actually allocate a block, rather either to allocate a block or to free a block. So this is the technique I used. Then sync fs bitmap, this is actually to write the bitmap to is, so once you modify the bitmap, you actually want to actually sync it back to the block. So in case if you have like a termination of our process, the bitmap is actually updated and actually is actually correct. Same thing as the inode bitmap, you also want to sync it once we actually update the inode bitmap to the disk, right? Once we actually update the inode bitmap, we actually want to sync it to the disk too. So find free inode. So this actually finds a free inode, that is that if inode that is free, not allocated, right? And this is actually going to be used when we want to actually create new inodes, right? And allocate free blocks, right? So these free blocks is the data blocks, right? I'm allocating these data blocks to each of the inodes. So each inode has a specific number of data blocks can have. So each inode, for example, inode 0 can have like 6 data blocks. All inodes can have a maximum of 6 data blocks. So that's what we are doing here. So I'm going to allocate about 6 data blocks to each inode. And free allocated blocks too. So once we are done with the inode, let's say we want to move an inode or want to move a file, for example, we can free the data block so another file can use it, those data blocks too. So that's another one. Then we have the read inode this block, right? These are try to actually this is actually one of the main functions, and this actually reads contents we want to actually put into our file system. So let's say we want to actually like write to a file, for example. This method is what, sorry, if you want to actually read from a file, rather, this method is what you actually call to actually read from that file. And write inode blocks right here is what we use to write to the file, right? We want to actually write to the file, probably from the terminal. So I'll show you an example of this. So want to write to the file, we call this method, right? We have fs formats too. So fs format is what we use to format our file system. So we initialize the super block and actually write it to disk or something like that, write it to the disk, right? So look at what happens here. So we read super block into super cache, initialize super block, right, to soup, and write it back to disk. There also like settings like initialize the fs bitmap, right? Initialize the bitmap, initialize the inode bitmap. They also mark all the bitmaps. So meaning that when we format our file system, rather, things like our super block, things like our inode blocks, things like our bitmap blocks, right? fs bitmap block and inode bitmap blocks, and things like indirect blocks are marked as allocated. So allocated means that this block are no longer free, right? They're already used in use. So if it's free, is 1. If it's allocated, is 0. So this is what we are doing here. So I'm marking all our blocks from block 0. I'm marking from block 0 so marking from block 0 to block 414 as allocated. So that's what we are doing here. So I'm marking from block 0 to block 414 as allocated. For inode bitmap, right? This is for here, rather. For this for loop here, I go to mark this, right, as allocated. Yeah, so mark this as allocated. So what I mean is that initially for this fs bitmap init, you know that I said that we made all blocks free. So once we have already formatted our file system, it's our job to actually make sure that all those physical blocks, all those should I say special blocks, are marked as allocated. So some process does not actually access those blocks, right? So it actually remains private. So next thing is that we sync fs bitmap. We also sync inode bitmap after I've made those changes, and our inode bitmap will still remain the same because at this point we've not actually created any file, so it will still be remain free, right? All sections of the inode will still, all the inodes will still remain free. Then so that's what this does. The fs mount just we use the super block, right? We use the FS bitmap block, we use the inode bitmap block, we use the iMode bitmap block to RAM, right? To a cache. So this is super block to super cache, FS bitmap blocks to FS bitmap cache, inode bitmap one, stuff like that. I don't want to be going into too much details, right? As it can be kind of confusing. But the general idea is just to get that we can format our file system, we can mount our file system, and we can also create files, right? So in this case, we have not implemented directories yet. So when you see fs create, we are just trying to create a file, right? So this is what this does. So to create a file, we first check to find a free inode, right? So right now, most of the inodes are actually like free. So inode 0 will actually is what will be returned here. That will be the inode index. So the first occurrence of a free inode is what we are going to return here. Then this is actually logic to actually get the position of the inode in the block. How did I do it here? I can't remember what I did here. Okay, yeah, to get the position of the inode in the block. So we just use this and we read this block into the inode cache. We access it, right? We access that particular inode and check to and assign this to a file. That this is a file. If I implement directories, we actually assign is a directory, right? Instead, and size is consequently 0. So once you create a file, the size of the file is automatically 0, right? And we know that the maximum size of each file in this our file system, in our own our simple file system is about just about I think that's about 24 KB, right? So when you first create a file, the file is initially 0 KB, right? We allocate free blocks to. So that means what we are doing here is we are allocating direct blocks to the inode, right? So we start from block 415. So block 415, let me just write this, block 415, 495 are data blocks. So we start allocating from block 415, 6 blocks for each inode we create, right? So this is the write block, this is the mark, repeat map, and stuff like that. Then we can also remove a file, and that's what fs remove does. We could check the size of a file. That's what this fs start does. I don't start going into explanation, right? Because I didn't really prepare for this. I don't want to just create a quick video to just summarize this. Probably in version 2, I'll try and break this down, right, better, right, and probably use better graphics and visuals to explain these things. Then we have fs read. So fs read calls on eventually calls on read inode these blocks, right? So fs read. So we want to read a file, we actually call on this. So this is the main logic for actually reading, right? This is the main logic for actually reading from a file, and it's actually up here, right? So this is what I was talking about, to read from a file. This is the main logic. Kind of long for an helper function though, but that's how it's actually implemented. So this is an helper function, and we actually read the disk block. So we're actually reading the disk block, trying to read the contents of the disk block. So that's what fs read does. Then fs write, we also call on write inode disk block, right? So you can see that in each of these places, we're also checking if fs is mounted. If fs is not mounted, we cannot call on these methods, right? So we have to actually always mount our file system before we can call on this method. And in turn, we have to, before we can mount, we actually have to format our file system. So I'll actually show an example of that, right? And fs destroy, right? Fs destroy just destroys our file. So we have to make sure we actually mount the file system, and we also have to make sure we free all our caches, right? So we don't have memory leaks. Then we close the disk finally. So that's just a overview of this. I know it might not be too clear, right? But probably in a later video, in a later blog, we have actually implemented directories. I've implemented stuff like directories, things like journaling, and other features of the file system. I'll actually try and explain this with better graphics and visuals so you can try and understand this better. But this is just a simple overview. So what you just know is that we can destroy our file system, we can read to files, right? We can read to files, we can read from files rather, we can write to files, we can create files, we can remove files, and we can mount our file system, we can format our file system. Then all these are just helper functions that we use, right? Like I said, these are like the main methods we have, right? The main methods we have here are the main methods we have here are fs mount, fs format, fs create, fs remove, fs start, fs read, fs write, fs destroy. So next thing we have is our shell, a shell-like interface. It's not really a shell, just a shell-like interface. So just to simulate to allow the user interact with our file system. So that's what we do. So our one is very soon. And so first thing, let's just run it now. So this is just our shell. So you can type in commands to actually do stuff, right? So we can format our file system, we can mount our file system, we can create a file, we can move a file, we can cut a file. That is, when we are doing a cut, we are reading from a file, we are reading to standard input. That's our terminal. Then when we are echoing a file, right, we want to actually write to the file where we echo a. This echo a means append, right? That is, means echo append, that is append to the file, right? So, and next thing, you can also copy from inode to inode, right? So we are copying from one file to another file. And we have stats, we have help, right? So this is what our simple shell does. So we don't really have to go too much into the details. Like I said, in the next version of the file system, I'll try and explain this better. So another thing is that these are tokenized input, right? So that's why I say this is like a shell-like interface. This is not a real shell. Normally, a real shell will actually create a process, right? To fork a process, to create a process, and to have proper ways of tokenizing our commands, right? In this case, we are just using like basic delimiters to actually tokenize our commands, but we should actually have a proper tokenizer that will actually help us to split our commands and to actually create processes. So that's what I'm going to implement soon enough. So let's just simulate the file system. Let's just see how the file system looks like, right, from the user's perspective, rather. All right, so first thing I want to build our file system. I want to build the project, rather. Okay, so we've created an executable called build pfs, right? And what I'll do is that I stored our disk in, I think I stored our disk. I'm correct, I stored our disk here. So this is where we stored our disk. So I will try and move the disk. What I'll do is that I will move /ssd data.bin. Yeah, so I'll move this. So once we do this, the previous command, we shouldn't see anything here. So I've already moved our disk. So now let's run our file system. So that is now, you can see that we want to run it. So one thing is that we should always pass the path to our disk, to this executable right here. So if we do this, we actually error out, right, because we don't have our path yet. So what you can do is that this is my path to my disk I'm creating here. So we have it in C-Lion. So I want to create a new disk, right? And what is, let me just use SSD, right? And let me just create a disk called data.bin. You can see we are now into the file system, right? We're in the file system like this currently, and things we can do, we can mount, we can format, right? So I told you that we have an order in which we actually do stuff, right? We have to actually format first, then mount. So if we try to mount before formatting, we can mount. We have to first format first. Then after we are formatted, we have to mount. So another thing is that we try to read, right? Let's say we have tried to like copy 0 to 1. File system is not mounted, so we can't actually do that. So we have to mount. The next thing is that let's say we want to copy from 0 to 1 to. So you can see that we are using numbers to represent our files. Normally, I meant to have like should I say parts, right? So something like let's say instead of having 0 1, you meant to have something like, let's say copy, let's say slash, let's say home /user, let's say file.txt, something like, let's say slash home / let's say read.txt or something like that. So we're meant to have something like this, right? So directory paths, right? But in this case, we're using our numbers representing, and this is actually the internal representation of the files, right? I told that these are inodes, so we're using inode numbers to represent our files. So when we start implementing directories, we'll start seeing stuff like this now. But for now, we just use inode numbers, which are actually represent files. So these are internal representations of our file. So at this point, we cannot read because we have not created inode, right? We've not created an inode, so we have to actually create. So create, I think this is what we just do. So we created inode 0. You can create another inode 2, so you can perform a read operation. So let's say we want to copy 0 to 1. So we wrote 0 bytes. So meaning that when we created the search for inode is 0 bytes. So currently our file does not contain anything right now. Both inode 0 and inode 1 does not contain anything. So let's try and write to the file. So I write it to inode 0 like this now. So you can see that we've written to this, right? So the file size is going to 26 bytes. So you can actually try and view the file, right? And this is a text, C is code. Then you can then copy from 0 to 1. So we're copying from file 0, that's inode 0, to file 1, right? So when we start implementing directories, to be clear, right, we start implementing like paths and stuff like that. But for now, this is just a simple file system, so we really want to make things too complex. But we start implementing directories to be clearer from there on. So now we can see that we've written about 26 bytes to inode 1. So initially inode 1 was 0 bytes, but we copied 26 bytes from inode 0 to inode 1. That is from this file to this file. From 0 to 1, we copy 26 bytes. So you can cut and see that we have the same thing in 1. Let's say we try to cut 2. So cut 2 is, so you know that inode 2 is not allocated, right? So you can create, right? Once you create this, you can cut 2. You can try and view what is in 2. And quality 2 will be what? 0 bytes. So we won't say anything, right? So that's it. So I just exited this. So let's try and inspect our bin file, right, to see what's going on. So you can see that this here, these are bin file, right, and these are data blocks, right, for each of the file. So it ranges from this address here to this address. This point here is our super block, right? These are super block right here. I know that because I've actually inspected the file. These are super block. This is the structs that we mounted here. So this here you are seeing here is this, right? This super block from here to here. This represent this super block. Then inodes, right, are this here. I think so. I think this should be our inodes, right? These are inodes, right? Then these are bitmap blocks, right? So this is first the inode, this is first the file system bitmap block, and this is the inode bitmap blocks, right? And these are data blocks right here. So I wish I could actually explain all this, like, and start breaking down all the X code to show that this is actually a super block and this is actually bitmap block. But should I say time is not there and video is already becoming too long. So probably in the later version of the file system, like I said, I'll try and explain things better, and probably with visuals, and we'll go deeper into file systems, create directories, implement things like journaling, do proper mounting, right, and do proper formatting too. So thanks for watching this video. This is just like a basic overview of a file system to understand how blocks are located, how inodes are created, and to understand that inodes are internal representation of files. So when we are creating a file, we are actually creating an inode internally, or if we are creating a directory, we are actually creating an inode externally. So all that is just the basic of how file system work. Thanks for watching the video, and we see you next time. Or we see you next time.